talk about digital gates. So the first gate that we introduced was the AND gate, right? So the number one is AND. So we could mention, okay, the AND is somehow a operator in Boolean algebra. How it works. So this is how it works. If you have two inputs, the first thing is the symbol that you use to show the AND gate is the symbol. Usually there is two inputs for that, X, Y, and Z. So two input, one output. So you have two inputs. So X and Y, each of them could be 0, 1. So that means you could have a 4 different beat pattern or 4 different scenario. Okay. So I'm actually list all possible beat pattern that we could make. Okay. So based off definition of the AND, whenever one of the input is 0, the output will be 0. So that means this is 0, this is the 0. The only case your output is 1 is whenever both of them is 1. So AND actually is one operator that we have in Boolean algebra and we use. How we could actually show that? We say X dot Y, which is in the Boolean algebra, we read that X and Y. Okay, so here this table shows how this operator works. Okay, so go to the next one. So which is the OR gate. Number 2 is OR. OR is the second operator that we have in Boolean algebra. The symbol that we use is the symbol that you see. It has two input, which is X and Y, and we have Z, okay, as output. So the symbol that you use to show the OR usually is you use plus X or Y. This is how we could represent this operator in Boolean algebra. Back to the table. So again, you have the same thing, X, Y, 0, 0, 1, 1, 0, 1, 0, 1. And the output is 0. Help me to finish this column that we have. So you already know these stuff from the lab. So if you OR 0 and 0, what should be the output? Type on the chat box. 0 or 0 is 0, right? So to complete this, how about 0 or 1 is 0 or 1, 0 or 1, 0 or 1 is 1. Again, 1 or 0 again is 1. 1 or 1 is 0. In other words, if one of them is 1, definitely output is 1. So this is actually the second operator that you have in Boolean algebra. Go to the number 3. So number 3, the third operator that we have is NAND. So NAND somehow is clear from the name. So first let's show the sample. So the sample that we use for NAND is the AND, that you have a knot or circle at the, yeah, maybe that's better to first, the third one should be AND to AND, then we could actually talk about the NAND. Okay, so before introducing the NOT, it's not good to talk about the AND. So I put actually third one as a NOT, which is another operator that you have in Boolean algebra. So the symbol of the NOT is the symbol that you see. Usually it is just have one input and one output, which is the Z. So the NOT of the X we usually actually show with X prime. So if you back to the table, the x is just could be 0, 1, and the z, which is x prime. Whenever it is 0, its prime is 1. Whenever this is 1, this is 0. Okay. So now we could go and talk about actually NAND. Okay. So let's do say NAND. So NAND, clear from the name, it is actually a and plus the not. So the symbol that we use is this symbol, which is the and one not circle at the output, which is tells it is the not. So technically, it's actually do the and between two inputs and then take a not all of that x and y. Okay, so usually the symbol that you use, you could actually say f or z. It is x and y, then the whole thing should be not. Okay. So if you back to the table, x, y is the input, 0, 0, 1, 1, 0, 1, 0, 1. So this is f or z, we could label f first. You need to take a and, the 0, 0, and is 0. If you take a not, you have 1. 0, 1 is 0, not is 1. 0, 1 is 0, not is 1. 1, 1 is 1, and its not is 0. Definitely, if you compare this with the truth table of the and, it should be exactly take not of this column. If you take a not of this column, should be give you an and, which is should be 1, 1, 1, 0, which is the same thing that you see here we have in the truth table of the NAND. So similarly, number 5, we could actually have another operator in Boolean algebra. Number 5 is NOR. NOR is clear from the name. So it is the OR gate, which is you have the not at the end. So as usual, you have two input, x, y, and the output is f. So what's happened here, you first OR x and y, then you take a not. So back to the truth table of the NOR. So you have x and y, 4 different bit pattern you could make, which you put here. So then here is the F. Just be careful. First the OR. So 0, 0 OR is 0. Take a not is 1. 0, 1 is 1. Not is 0. 0, 1 is 1. Not is 0. 1, 1 OR is 1. Not is 0. So that means it should be similar with the OR truth table. Just you take a not from these columns. So that means you should have 1, 3, 0, which is you have the same thing here, 1, 3, 0. Okay. So we label that as a operator number 5 that we have in Boolean algebra. So go to the next, number 6. So number 6 is XOR. So the XOR, the symbol of the XOR is the symbol that you see here. So you have two input, x and y, and the output is f. And usually you use this sign as a XOR. So you see, you say x. This is the symbol of the XOR, which is some 1 plus inside the circle should be the XOR. Okay. So this is XOR. Take a look to the table and see how it's works. So again, you should have 4 different bit pattern in one side of your truth table. So the XOR is whenever the both of the input is same. If I call this F, the output is 0, right? And whenever the both side actually is both is same is 0. Whenever they are different is actually is 1. Okay. So that's what we call actually the XOR. So the next operator, so because you already know this stuff, I'm just review a little fast. So this is 6. Let's go to the 7. So the 7 is XNOR. So the symbol of the XNOR is clear from the name. It should be XOR, which you have some not at the end. Okay. So again, you have X. This is Y. The output is F, and F is XOR of the X and Y. So this is a symbol we use to show the XOR in the Boolean algebra. One circle, one dot in the middle. Okay, so this actually means XOR. So take a look to the truth table. You have X, Y as the input, 4 different bit pattern you could make. And definitely should be not of these column that you have. So that means here it should be 0. If you XOR 0, 0 is 0, you take a NOT is 1. So here XOR is 1, NOT is 0, 0, 1. So the C, it is similar with whatever you see here for the XOR, just I take a NOT of that, which we call that XNOR. And the final things that we have, which is we label that as a number 8, it is a buffer. Buffer is almost similar to the NOT, which is just has one input. If input is the X, the output is the same X. So if I add actually the truth table, X just could be 0, 1, F equal to X. Whenever it is 0, it is 0. Whenever it is 1, it is 1. Somehow maybe you actually ask these questions. So why we are doing this? We actually get one input, we are doing nothing, and the output is the same thing with the input. So there is some application for that. Sometimes in the digital system, you want to make a delay. Okay, so that means you want to one output or input you want to actually send with the specific delay. So in that time, you could use the buffer. So somehow it's actually give a delay to transfer these X from input to output. The second application is sometimes depend on the circuit, you want to somehow isolate these two parts. Also, they are both X, but with using the buffer, you actually isolate these two. That means if something goes wrong in the right side, it's not going to affect whatever you have on the input. Okay, so that's actually the second application of the buffer.